In this video, we begin our study of Chapter 9, where we'll look at models of chemical bonding. We'll first look at atomic properties and relate what we've learned in our previous chapters to chemical compounds. We'll look at ionic bonding and covalent bonding and metallic bonding. And along the way, we'll discuss something called electronegativity and the spectrum of behavior from ionic to covalent to metallic to ionic bonding. And at this point, we're very familiar with the periodic table. And as we look at it here, we've got in blue the metals, in green are the metalloids, and in yellow are the nonmetals. What we learned from the last chapter is shown in the right-hand table. The metals tend to have larger atomic sizes. They have a lower effective nuclear charge. They have a lower ionization energy and smaller electron affinities. In contrast, the nonmetals are smaller atoms with higher effective nuclear charge, higher ionization energies, and larger, more negative electron affinities. And this affects how they participate in chemical reactions. Ionic bonding, as we've discussed previously, involves the transfer of electrons and is usually observed when a metal transfers its electrons to a nonmetal. So a metal plus a nonmetal gives us an ionic compound. And in this video, we'll look at this in detail and see what drives this process. Next is covalent bonding. And in covalent bonding, we have sharing of electrons and is typically observed between two nonmetals. So a nonmetal will bind with another nonmetal to form a covalent compound. And finally, we have metallic bonding. Metallic bonding is what occurs between two metals, either between two metals of the same element or between two different metal atoms. And in this case, the large size of the metal atoms and the loose attraction of the outer electron creates an electron pooling, which in some sense is similar to covalent bonding, yet it's different and unique. The electron pooling with the metals tends to be delocalized or shared amongst multiple atoms, as opposed to sharing between two atoms. If we have two dissimilar metals, when they bond together, we form a metal alloy. Here's a graphical representation of these three processes. In the left-hand box, we see sodium as a metal reacts with chlorine as a nonmetal. The electron on the outer shell of sodium is transferred to the chlorine to form chloride, and the smaller sodium cation then binds with the chloride anion. And as we'll see later, this last step is the driving force that results in the formation of ionic compounds. In the middle slide, we see the interaction between two nonmetals. We have a chlorine atom interacting with a bromine atom to form the compound bromine chloride, BrCl, a covalent compound. It's a gaseous molecule. And in the third slide, or the third panel, we have metallic bonding, and here we see these sodium atoms in a piece of sodium metal. The sodium metal is held together by chemical bonding, and that chemical bonding occurs when those outer electrons on all the sodium atoms are delocalized across all of the nuclei. This triangle illustrates the spectrum of bonding that occurs. We sometimes think of ionic, covalent, and metallic as being three very discrete and distinct types of bonding. But in reality, there is a spectrum of behavior. Let's look across the bottom side of this triangle to illustrate this. We have a series of pairs of atoms that can interact among the period 3 elements. So we start off on the left-hand side with sodium on the far left-hand side of the periodic table in period 3, and chlorine in group 17 on the right-hand side of period 3. When sodium and chlorine interact, they form an ionic compound. Next, we have sodium interacting with sulfur to form sodium sulfide, which is an ionic compound. Next, we have sodium phosphide, and that's ionic. But in the solid state, it starts to show behavior that shows slightly metallic behavior. Next is sodium silicide. Then we get to sodium aluminum. So a sodium aluminide is an alloy. And in this case, we have metallic bonding, but there is some unequal sharing between the sodium and the aluminum atoms. Then next is sodium magnesium alloy. And then finally, sodium metal. And in sodium metal, we have truly metallic interactions because the atoms on both sides are equal, so there will be equal sharing across all of the atoms. On the right-hand side of our triangle, we can look at the transition from metallic to covalent interactions. And the elements in black represent period 3. So we can see at the bottom we have sodium, and sodium shows metallic behavior. That very loose electron, that very loose 3s electron is delocalized across the entire lattice. Then magnesium, with the 3s2 electrons, we have a little bit more stronger interaction between the magnesium atoms. That's a much harder metal. Magnesium is a much harder metal and is used as a structural metal, whereas sodium, and this is on top of its high reactivity, is a very soft metal. And next up is aluminum, and then silicon. And silicon is a semiconductor that is showing covalent bonding in the solid state structure, and it's a much more rigid structure that does not delocalize and does not deform nearly as readily as aluminum or magnesium or sodium. So silicon really represents the transition from metallic to covalent, where we're having covalent interactions within the solid state structure. And then phosphorus shows much more covalent interactions in the solid, as does sulfur. And then finally chlorine, which does not form a solid at room temperature. It's a diatomic gas. On the third side of our triangle, we see the transition between covalent and ionic interactions. In this case, we're looking at compounds involving in the red our period 4, our group 4, 14 elements, the group 14 elements, or group 4A, so carbon, silicon, germanium, tin, and lead, bonding with fluorine. So the element at the top of group 14, carbon, when that interacts with fluorine, we form carbon tetrafluoride. Carbon tetrafluoride is a covalent compound. Next up, we have silicon tetrafluoride, which is very covalent in its properties, but has more polarization in its bonding. Then we have germanium fluoride and tin 2 fluoride and lead 2 fluoride, which are much more ionic compounds. And correspondingly, we can look at the diatomics or the interaction between two elements along period 3. So we can start with chlorine, then going to sulfur dichloride, phosphorus trichloride, silicon tetrachloride, aluminum chloride, magnesium chloride, and then sodium chloride, showing the transition from covalent to ionic interactions. And it's clearly a spectrum of behavior, as each compound shows progressively more ionic property as we move from chlorine down to sodium chloride. When we go to represent compounds, we're going to use something called Lewis dot symbols. or electron dot structures. This is named after G.N. Lewis, one of the greatest American chemists who did not receive a Nobel Prize for political reasons, but was nonetheless a great American chemist. And he developed an approach to symbolize the chemical bonding within main group elements. And so we have what we call Lewis dot structures or Lewis symbols. And for each element, we note the A group number, which we've not really talked about a lot, but rather than, for example, using group 14 for the carbon group in the periodic table, we can call them group 4A. And if we use the 4 group, that tells us the number of valence electrons. You could also determine the number of valence electrons because you did that as an exercise in our previous chapter. We place one dot at a time on each of the 4 sides of the element symbol to make a Lewis dot structure. We keep adding dots, pairing them up until all of them are used up. So we can take, for example, nitrogen. Nitrogen has 5 valence electrons. That's a 2s2, 2p3. It's in group 5a, so it has 5 valence electrons. And we can arrange them any of these 4 ways. They're all equivalent to one another. But these are representations showing 1 pair of electrons and 3 individual unpaired electrons. So Lewis symbols are very nice for illustrating chemical bonding, particularly for organic compounds. It's very powerful for organic compounds, and you will use Lewis symbols on a daily basis when you get to organic chemistry. Organic chemists use them, and they are very good for describing organic compounds. Now, for a metal, the total number of dots that you draw in the Lewis symbol is the number of electrons that the atom loses to form the cation. So if you have something with maybe more than 2 electrons, but you only form a dication, we just write down the 2 electrons that are involved in reacting. And for the nonmetal, the number of unpaired dots equals the number of electrons that the atom gains to form an anion, or the number it shares to form covalent bonds. Now we have something called the octet rule, and if you've had a high school chemistry, you may have heard this before. The octet rule states that when atoms bond, they lose, gain, or share electrons to attain a filled outer level of 8 electrons, or 2 for hydrogen and lithium. Now the octet rule is really great for organic chemistry. Pretty well holds for every organic compound, and there are literally tens of millions of known organic compounds. And in general, the octet rule works quite well for the second period. So it's not just carbon. It works well across the period. It's not so great for boron, but for carbon, nitrogen, oxygen, and fluorine, it works quite nicely. But it's less applicable for other main group elements. It does work in some cases, but in many cases it does not. And we'll see those. We'll go through those when we get to chapter 10. And it's not at all applicable really for transition series. We have something called the 18 electron rule. We won't go over the 18 electron rule. That's taken in, you'll cover that in more advanced inorganic chemistry courses. Here are Lewis dot structures for elements in periods 2 and 3. So you can see lithium has 1 valence electron, so we draw it with 1 dot. Beryllium has 2, boron 3, carbon 4, nitrogen 5, oxygen 6, fluorine 7. And neon, which we generally don't draw because it has no important or significant chemical compounds, it would have 8 electrons. And similarly for period 3, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and then argon. These are nice for period 3 for some small subset of compounds. But for example, you can think of compounds quickly like sulfate or perchlorate, where things would become much more complicated because there's multiple atoms around that central sulfur or chlorine atom. But for period 2, this dot structure becomes a very powerful tool. Now let's start looking at the ionic bonding model, and that's what we'll spend the rest of this video talking about, is ionic bonding. An ionic bond is formed when a metal transfers electrons to a nonmetal to form ions. Now let's take the first part of that sentence before we look at the second half. We think of a metal as losing electrons fairly readily, and ions as nonmetals as gaining electrons to form anions. But that process in and of itself actually requires energy. The ionization energy of a metal is greater than the electron affinity of a nonmetal. What really drives the formation of ionic bonds is those ions which attract each other after they've formed to give a solid compound. Total number of electrons lost by the metal atoms equals the total number of electrons gained by the nonmetal atom, and we would know that because of electroneutrality. So we can look at lithium interacting with fluorine. We could write electron configurations. 1s2, 2s1 for lithium, and then 1s2, 2s2, 2p5 for fluorine. And these will result in lithium going to a 1s2 and fluorine to a 1s2, 2s2, 2p6 to form our corresponding cation and anion, respectively. You can draw them as orbital diagrams to show this, or we can use Lewis dot symbols. All these simply show the process that I think you'd be comfortable with now. The metal loses an electron, the nonmetal gains it. But remember, this step alone is endothermic. It takes more energy to pull an electron off a metal than the nonmetal gains by picking up that electron. The real driver is lithium has a positive charge and fluorine has a negative charge, and that plus and minus attract each other together to form an ionic bond. So here's a picture of what happens if you take sodium metal, and that's shown in the in panel A. The sodium metal is the grayish solid at the bottom of the beaker. That's in oil. That's not in water. If it was in water, it would react violently. That's in oil, and the oil is there to keep water away from it. If you take a chunk of metal out of the oil and drop it into the round flask next to it, the round flask contains bromine. Bromine is a liquid at room temperature, but it has a very low boiling point, and so there's a lot of bromine vapor above that. So you can see the brown color is the bromine, Br2 gas, in equilibrium with the liquid. And if you drop that sodium metal in there, you get a lot of heat and a lot of light. The ionic compound formation from elements can be very exothermic. In fact, some of the most exothermic reactions we know of are metal plus nonmetal to form ionic compound. And this figure, where we're going to take some time to walk through this, this shows what the driving force is. This is an energy level diagram. So on our vertical axis is enthalpy, that's H. So we're familiar with this. And each line, each horizontal line in this represents a step in a chemical process. And this is what's called a Born-Haber cycle. It's a thermodynamic cycle. You can start at any line and you can take all the individual steps, and if you go around the circle all the way and end up at this place you started, the total energy change will be zero because it's a closed cycle. Closed cycle processes like this have net enthalpy changes of zero. Let's start at the thick black line. The thick black line shows us lithium solid plus 1/2 of a mole of fluorine gas. So that would be the reactant pair that would result in formation of lithium fluoride. So I take lithium metal, fluorine gas, react them together, and I get lithium fluoride. So the big black line, big black arrow going downward, shows us the exothermicity of this process. That's the enthalpy of formation of lithium fluoride solid. Now, let's go back up to the lithium solid plus 1/2 fluorine gas, we can go upward from that, and that small orange arrow that goes up to lithium gas plus 1/2 mole of fluorine gas, the enthalpy for that process is the sublimation energy of lithium metal. That is, taking lithium from a solid directly to the gas. Silberberg has written delta H0 atom. That's the atomization energy, but that is equal to the sublimation energy of the metal. The next step is taking lithium gas, and lithium gas doesn't change, but taking 1/2 mole of fluorine gas and converting it into 1 mole of fluorine atoms as a gas. And the enthalpy for that process is 1/2 of the bond energy of fluorine. So you're taking fluorine molecules and breaking them up into fluorine atoms. And then the next step, now we have a lithium atom gas and a fluorine atom gas. I can take and I can remove 1 electron from lithium. So that's the first ionization energy of lithium. Remember that from back in chapter 8. So that's a nice big number, and that gets us up to lithium ion gas plus fluorine gas. And there will be an electron there also. And then we can take that electron and stick it onto the fluorine gas to give fluoride. And that step is exothermic, so the arrow goes downward. So we're at the very top black line going downward to now lithium plus gas plus fluoride minus gas. So before we take the last step, let's go to the very bottom and look at lithium fluoride again. And we're going to go through this cycle clockwise. So as we go clockwise, we go to the elements, then to lithium gas, then to fluorine gas, then to lithium ion, and then down to fluoride ion. So now we have lithium plus fluoride. The last step is a very large step. So that's the biggest step in this figure. So that we're going in our figure, we have an arrow going downward that shows lithium plus gas plus fluoride gas goes down to form lithium fluoride solid. And the enthalpy for this process is minus what's called the lattice energy of lithium fluoride. So the lattice energy of lithium fluoride, would be going from our very bottom black line, the lithium fluoride solid, in the opposite sense of that orange arrow, up to lithium plus fluoride minus, both as a gas. So as you look at this cycle, we see that if we take our thick black starting line, that is lithium solid plus 1/2 mole of fluorine gas, it's exothermic to form the crystal. It's not exothermic to form lithium ion and fluoride ion. That's actually endothermic, but it's the last step over on the right-hand side where those ions now coalesce to form the crystal that is the energetic driver for this process. So the big energetic driver for this process is the combination of the metal ion gas and the non-metal ion gas to form the metal, non-metal solid crystal. And that driver is minus the lattice energy of this process, minus the delta H of formation, delta H0 of lattice of the ionic compound. So let's look at this idea of lattice energy. What is lattice energy? Well, number one, this is the bond energy for ionic compounds. We'll find out it's a really big number. Those bonds are very strong, and it cannot be measured experimentally. So you cannot measure this directly. We have to actually do calculations to deduce what it is. In order to obtain or to determine what lattice energies are for ionic compounds, we have to use thermodynamic cycles. This is one key place where Hess's law, remember back in chapter 6 when we talked about Hess's law, combining reactions to figure out ones we don't know, this is one of the key places where Hess's law is applied. So we're going to do this right now. Hess's law in action is going to show us how we use things that we can measure to determine the lattice energy, which is something we can't measure. So for lithium fluoride in the last slide, we're going to go clockwise, and we're going to start at the very bottom line, that is from lithium fluoride solid, and we're going to write out all the reactions. Reaction 1 is lithium fluoride solid going to lithium plus solid, or excuse me, lithium solid, not the cation, just lithium solid, plus a half a mole of fluorine gas. What is the delta H for that reaction? Well, it's minus delta H of formation of lithium fluoride. Step number 2 is taking lithium solid and lithium gas and taking it to lithium gas. That is the enthalpy of sublimation of lithium solid. Number 3 is taking a half a mole of fluorine gas, that's diatomic fluorine F2, and converting it into fluorine atom gas, 1 mole. And the delta H for that process is 1/2 of the bond energy of fluorine gas. Step 4 is taking lithium gas as an atom and converting it to lithium ion as a gas plus an electron. And we know that that is, the enthalpy for that process is the ionization energy of lithium. That's the definition of that process. Finally, step 5, we take the fluorine atom gas and add an electron to form fluoride anion gas. That's the definition of electron affinity. So if we add those first 5 steps, then lithium fluoride solid going to lithium ion gas plus fluoride ion gas is the sum of all those. And if we add those 5 delta H's, they give us the lattice energy for this process. So if we add all 5 of those first 5 reactions together, we'll get a large positive number. So we note that steps 1 through 4 are all endothermic. Only step 5 is exothermic, and it's not a large exothermic value. It's a small exothermic value. So all these add together are a large positive number. So the lattice energy is the large positive number. And minus the lattice energy is the driving factor that makes crystal formation stable. It's the reverse of that process. It's bringing the ions together into a crystal because of the positive and negative ion attraction for one another. So you've heard the phrase opposites attract. Well, in this case, that's actually true. Opposites do attract. The cation and the anion are attracted to one another. What are the things that affect lattice energy? Well, we know lattice energy, by definition, is the energy required to separate 1 mole of an ionic solid into its gaseous ions. It's a measure of the strength of the ionic bond, so it is the ionic bond strength. And so we see that since this is an electrostatic interaction, Coulomb's law will tell us how this will work. Electrostatic energy, which is related to the bond energy, depends on the charge on each of the ions divided by the distance between the ions. And the distance between the ions depends on the cation and the anion radii, like we learned in Chapter 8. So the lattice energy then should be larger for larger charges, and it should be larger for smaller radii. So indeed, we see the lattice energy is affected by ionic size and ionic charge. As the ionic size increases, the lattice energy decreases, because as the ions become larger, they can't get as close together. The lattice energy, therefore, decreases going down a group on the periodic table because we know that the ionic size increases. And in general, as ionic charge increases, the lattice energy increases. And we can see a very clear example of this here in this figure. On our vertical axis, we have lattice energy going from 0 up to a very large number, 1100 kilojoules per mole, or 1.1 megajoules per mole. That's a big number. And we have 4 alkali metal cations: lithium, sodium, potassium, and rubidium. Lithium, of course, is the top element in the alkali metal group among the metals, not including hydrogen. And lithium, hence, is the smallest. And since it's small, it can get closer to all of its negative ions. Therefore, its lattice energy is stronger. It can get closer and hold more tightly. Going across the bottom, we have the halide series: fluoride, chloride, bromide, iodide. And of course, those atoms show the standard increase in ionic radius from fluoride all the way up to iodide. And so if we look, the black dots then represent the lattice energy, and the ionic compound in this group here that has the largest lattice energy is what you'd expect: lithium fluoride. It's got the 2 smallest ions. Lithium fluoride has a larger lattice energy than does lithium chloride, which is larger than lithium bromide, which is larger than lithium iodide. And the same thing goes for the sodium salts, the potassium salts, and the rubidium salts. And the smallest lattice energy of the entire group of compounds is rubidium iodide, because those are the 2 largest ions paired together. So given that we have a very large lattice energy, that tells us the bond energy is really high. That means the ions are held together very strongly. So they're very tightly held together. Therefore, as we think about the properties of ionic compounds, which we know that tend to be very hard, very rigid, and very brittle, and they have very high melting points. And that's consistent with this strong ionic bonding between the atoms, or the ions, within the ionic compound. The ionic compounds do not conduct electricity in the solid state, because in the solid state, the ions are fixed in place by that large ionic bond strength, that large lattice energy, and so they can't move. But once ionic compounds are dissolved in water, or if the ionic compound is melted and put into a molten state, then electric current is carried very readily. They're electrically conductive because the ions are free to move and they can carry a current. Now, the next thing is we want to look at is the reason for the brittle nature of ionic compounds. If you take a piece of rock salt and you hit it with a hammer, it'll shatter into little pieces. This would contrast, for example, with a piece of lead. So if you have a lead sinker, for example, if you go fishing and you have a lead, sometimes we use lead as a sinker. If you take the lead and you hit it with a hammer, it smashes out just like Play-Doh. And so why do the ionic compounds shatter? This figure illustrates that. On the left-hand side of panel B, we see the ionic crystal lattice. And then we see a force comes in to dislocate the atoms within the crystal lattice. As soon as we move from one lattice plane to the next one, we see the positive ions are now lined up with the positive ions, and the negative ions are lined up with the negative ions. And these 2 charges are alike, and they repel one another. They push away. And therefore, the crystal will crack apart. We're going to look later on to see why something like lead and metals don't do this. So we saw this earlier in one of our chapters. This is a figure that was very similar to what we saw earlier, just showing why we have conductivity in the solid ionic compound. There's no conductivity because the ions are frozen. When we melt the ionic compound, the conductivity jumps up because the ions are now free to move in the liquid state. And once they're dissolved in water, they're likewise able to move in the aqueous solvent. Here are melting and boiling points of some ionic compounds, and you can see that they're quite large numbers. There are some that are even higher than this. They're very, very high values. And you often use use ionic compounds in ceramics or for bricks in high temperature furnaces because they can withstand very high temperatures without melting. Aluminum oxides, magnesium oxides. Typically, you're looking when you're working with ceramics for bricks for high temperature furnaces, you want something with a really high lattice energy because a high lattice energy will have a higher melting point. So you want a small atom with a high charge. So something like magnesium, for example, has a +2 charge. Oxygen's a small atom with a -2 charge. Or similarly, another one that's used a lot is aluminum oxide. Aluminum has a +3 charge. Oxygen with the -2 charge. Those are very high melting point solids. Things with high melting points are very stable. Things with high lattice energies have high melting points. They're very stable and very hard structures. One final point, when we do melt ionic compound, we have ions that can move freely in the liquid state. If we take the solid or the liquid to a high enough temperature to get it to boil, the ions don't come off separately, they come off as ion pairs. Because that positive-negative attraction is so strong that you can't break it up even when you boil it. Interionic attractions are so strong with an ionic compound that when an ionic compound is vaporized, ion pairs are formed. In our next video, we'll move on to covalent bonding interactions.